This is a recording that goes with the second programming assignment using subroutines that I created, and has the purpose for the students to practice their programming skills, things that you've learned in other classes and using MATLAB. And I understand some of you have been exposed to writing code to program Arduino microcontrollers. Okay, so with this second assignment, you receive a source code that you have to modify it to get your punch press crank slider mechanism operating vertically. If I'm compiling, and build means everything is compiled, and then run this program, you will see an eccentric slider crank mechanism with the slider moving in a horizontal direction. There are functions, there are subroutines in the program that you're familiar with. The crank, I removed the shape that moves with the crank, the one that I asked you in the first assignment to edit the fillet radii at the outer end. But there are elements there that are present in this program, which I made by just adding lines of code. So the crank is the same, current angle measurement is the same, the reference frame XY is the same, no shape. And then in order to do the slider simulation, you need to call a subroutine that is a building block in a SUR group that does the kinematics of a link with a slider sliding about the direction, and the direction can be movable, not just fixed. And in addition, using the same function, put angle, it measures the transmission angle, as you can see, and also it's a new function, put distance, that measures the displacement of the slider. Okay. So let me stop this. I bring up as you can see, this icon and press the escape key, or rather you need to click on it to make it active and press the escape, or it should. All right, so finally it stopped. The reason why the simulation continued past one cycle is because I have this repeat until while do loop. So I'm deleting this, and so you won't see them in the source code from me, and delete this one as well. KY does the line delete that you selected. And if I hit run again, what it does is just running once and it stops by itself. Okay, so this is what you will get from. Okay, so and there are some comments, and of course you'll be placing your name there. I inherited some of the questions, and you have to populate the comments here. So what's omega? Everybody knows that, I'm assuming. These are and there are some other changes. For example, the crank length was named R1 earlier. Now I changed it to R2. We're familiar with R1 being the eccentricity. Connecting rod length, if I run the simulation again, you can see its name is AB. Okay, and then there's the point P here, and there's a point Q here. So sliding occurs along the line from P to Q. So I'm asking you what P and Q are. I already told you. What XB, YB, VXB, it's the time derivative of XB, VYB, time derivative of YB, and these are the acceleration X and Y components of the acceleration of point B. Okay, this is the transmission angle, slider displacement. The way the mechanism is configured is that displacement of the slider is nothing but Y of, X. Y would be your case of the slider. This is because it's moving on a horizontal direction. If the direction would be at some angle, then I'm going to introduce you to a function that is, or a subroutine that is not used in this program, but those interested in practicing with the collection of subroutines that I'm providing you with may want to like I said, to experiment with. Okay, so in addition to delta, if you remember, when solving the kinematics of the slider crank, there is a quadratic that you have to solve, and the delta of the quadratic has some relevance because its values change, and it's getting closer to zero when the mechanism is in its limit positions. Okay, so and then lastly, it's separate. So these are variables of the double or real type, and this is a text file. FT, it's a text file. ASCII or text file is the same thing. So I select KH, takes the selection off, or just click outside. Yes. So what we do first in the program, it starts and ends with begin and ends with end with a dot. That's the end of the program. So what it does first, it's assigning this name, crank slider, an extension DAT, its data, to the FD text file, and then rewrites, opens for writing, rewrite FD. If there's any text with or dat file with this name, is going to be rewritten. It's lost. So if you play scenarios, you want to either change the name or you copy elsewhere the crank slider already existing file. Okay, this is the header to the dat file. First line, it's explaining T theta 2 in radians, in a second line, time in second, crank angle in radians and degrees, crank displacement as rather slider displacement, I'm sorry, in whatever units you assume the linear variables to be, and then time derivative of S and second time derivative of S, and finally theta 3 in degrees. Okay. From the crank program, same statements. Although remember, I changed. Originally it was R1. Now I changed it to R2. Crank length, slider eccentricity, length of con rod, connecting rod AB, and the I'm no longer using XO and YO for the origin. They are just 0 and 0, so they are implicit. They no longer occur as XO and YO being directly or replaced with 0, or that 0 may not even show. So you need to pay attention to the way these zeros have been, that is the origin or the about which the crank rotates, have been used or defined. The same as for the simple crank mechanism. This is where you define the limits of the workspace, and I used tried to make the program a little bit more flexible. If you change the length of the radii, but you can put values here. Really, you can make them knowing what the limits of the workspace is. So I could make this, for example, I don't know, 3. It's x min x max minus 3, and probably here I would need a 5. Could change it, and then y limits could be from -3 to +3. Let's see what the difference. So yeah, it's too small, or rather the limits are too big. So let's change it to just maybe 0.3, 0.5, or just 1, and 0.3 and 0.3. Okay. All right. So looks a little bit better. but smaller than before. The proportions or the size of the motor symbol, the joint, and the slider and the joint again, as well as the ground, 3 hatches showing the ground connection, are governed by the set joint size. So if I change this to 3, it will look much smaller. Okay, as you can see here. Text font size stays the same. So let's make it whatever was it, 9, 7. DXF file where the various layers, each layer to one simulation frame, are written. I told you DXF files are text files. The nice thing is that you can open them in AutoCAD and you can select the layer corresponding to a position that you are interested in. Part of this assignment, you will have to generate or select the layer showing the mechanism in its minimum maximum transmission angle positions. Okay, so I have number of frames, number of positions, frames, yes, 73. That corresponds to a 5-degree increment. So if you trade 360 full cycle and divided by 5, it gets you 72. But because we also take a 0 position, see the I plus minus 1 here, so I have to add 1. So 72 goes 73. If I want to make or 1 frame per degree, it has to be 361. Okay, so 73 was there. We leave it as is. Okay, and then the main for loop and new frame. It clears the screen for a new drawing. Current time, again, it starts from 0 because I go from 1 to number of positions, but subtract 1, so this time will be equal 0. Current angle of the crank angle, it's function of omega, angular velocity. If you take derivative of t times omega with respect to t, it gets you just omega. Omega is constant. If you take derivative of a constant, it gets you 0. So these are consistent. If you do some work for other application, that might interest you, you need to make sure that in order to get correct results all the way to accelerations, that derivative of theta input of the input is a true derivative. Just make numbers here. And likewise, so you may have a crank that rotates other than the constant rate. You might have a sine function here. I can do that, no problem. I can make the sine of t, let's say pi times, let's see what happens. Okay, so it slows down and reverses. Well, let's say instead of, okay, so again, and then reverses. Okay, but the thing is that the thing is that so if you take derivative of theta 2, you don't get omega. Okay, so be advised, if you want correct results for all the way to velocity and acceleration, you need to have the derivative of theta 2, the correct derivative, second derivative of theta 2, correct derivative. Okay. You've seen this. Again, I took the link off, so there's no shape moving with the crank. You've seen this one, and this one. This is new. This is where, and very important, this is the Assur group, and it's a simplified version of it. That's why the 0. A more general one would be where there is an offset. I need to run it again. There is an offset here between B, the center of the slider, and where joint B is. But this is a centric, you could say, the centric dyad RR prismatic or RR translation, rotation translation. So clearly the color of it and what you supply to the subroutine are coordinates and their first and second derivative of 1 point, and then you need to give the line of sliding. So it's xp and yp. Okay, and these are fixed points. I could make them moving points You know, I could run the slider about a second crank that rotates. That's also possible. Very powerful. But the zeros means that the derivative of xp and yp, first and second time derivatives, are zero. So these are fixed points. And then r3 is the length of the slider, length ab, +1 or -1. This makes the mechanism assembling has been taken care of for the right side assembly, okay, by just changing for +1 to -1. And these are outputs, so xb, yb, and their first and second time derivative, as well as that delta that I told you, and has a value. If you're interested in a little bit more fancy studies, you can plot, you can inspect delta. Actually, I'm going to change it and put the delta part of the output to the text file. And then okay, so put G point, it means put a ground point. The ends of the line of sliding, they show on the simulation, so like right here and here, the points. And then what else? Put distance. And put distance is taking care of this dimension. And as you can see, you can here it's the number of spaces makes the length of the text. Well, I need to wait for a full cycle. Okay, so I can reduce. And if I want to have arrows at both ends, you can change it so you can see error and error. Maybe if I change the size of the joint to a bigger size, like it was 9 before. And also, let's see, if we look at the limits, if I make the limits a little bit smaller, 2 and 2 and 2, let's see, does it look bigger? It should. Yes, so error head. If I don't want an error head, you skip that. So I could make the 2 error heads for the put angle part. Put distance again was without. And then S, it says here last dim value. I could, and it's used again here, last dim value. So once you call put distance or put angle, there is a variable that you can, that's called last dimension value, and you can assign it to a local variable. Of course, if next time you call either put angle or put distance again, it gets refreshed. So you need to do this kind of saving of the value right after it, okay, or after calling put distance or put angle. So I could do it. I could do it likewise here. To what does not help. I'm just getting back theta 2 that I know. There are functions that can get you not just the linear value, but also first and second time derivative. But they are not part of this program. I'm just telling you they exist. I'll mention them at the end. So okay, so we have S. And I'm fast forwarding a little bit. This is the very end. There's of the for loop. So I have for loops starting here and ending here. The end of right before the end of or the for loop repeats or end the for loop. Yes, I write here to file to FT to the ASCII file. And this is formatting, so the length of the string that's written is 9 positions and then 2 blanks, and then more stuff written to the text file. So what do I write? I write time, I write theta 2, I write theta 2 times DEG. It converts by multiplying by DEG, converts theta 2, which is in radians. The way it's calculated here is in radians, to change it to degrees. And then S, the way it was saved here, it's written to file on whatever position, 1, 2, 3, 4th position, it's S. And then you don't see a DS and DDS slider moving in a horizontal direction. Actually, displacement and velocity and acceleration of the slider would be the and because the crank is, well, we measure from the origin. So yes, we have velocity of in the x direction of b as slider displacement, acceleration of point B in the x direction as second time derivative of s. So I could replace this with xb, and no need for this line of code, and we'll get exactly the same thing. Okay. Well, difference will be visible to the DAT, the output file. Okay, so, and this is it. Once the full cycle is ended, it stops by itself. You need to take care of closing the text file. You need to take care of closing the DXF file. And what this does is just cleaning some temporary files and closing the graphical window. Okay, so this was pretty much it. Like I said, I could also write to file delta. I'm telling you now, if there's something that you are not in, so say you want to do just position, and you don't care about velocity and acceleration, unless they're 0, and you need to put zeros. But other than that, for example, if I don't need the delta, I can just put this placeholder. And of course, it does not make sense now to write delta to file. And elsewhere. So for example, I'm not interested in the velocity and in the acceleration of point B. I don't need to define variables VXB, VYB, AXB, XYB. I can just put underscores, this placeholders. So this was A, Y, B, okay, and this was delta. Like right now, the way you see it, and it's the way you in the end you'll have this source code presented to you. There's also a delta there. Okay, so let me run it one more time, and we can look at the where am I? So we go to FPC and we go to MSD, and I have a lot of stuff here, but these are old, the backup copies. Crank slider, okay, the DAT file, and yeah, so time, theta tuned, radians, degrees, remember the header. This is delta, of course, and you can copy this, and we can go and make it the new KY. It deletes it, and then I go edit and paste from Windows. All right. So now, next time I'm running the program, there will be a delta will show there with in the header. Okay, so every 5 degrees is promised, going all the way to 360, and okay, 360. And you can open this in Excel. I assume you know how to open text files in Excel. Your notepad might not be configured to open DAT or other extension than TXT files. I'm sure you know how to make it open other file. I can open with Notepad anything. I can open a PDF file, for example, if you're curious how it looks like, as well as pass files. So open with, and my default is Notepad, and I can inspect source codes. Okay, so this being said, I can move to units, and here are the libraries. So Assure2, and what we used is the what was it? RRT0, which is an abridged version of RRT. These are slight different. They're the same rotation translation, sort of isomers, or depending on how the slider and its guide are configured. You either move the sliding block relative to a sleeve, or you move the sleeve relative to a sliding block. That's the only difference. But we use this one, RRT_0. It's a shorter version of the one on top. This one again has an eccentricity built in. It's like imagine an engine, and the piston pin is not running along the axis of the cylinder, but rather runs at some offset. Okay, so that's for the main subroutine that does the kinematics of the slider. And then what else we have? In this one we have, okay, so I'm sure you've been here. So and I maybe should have emphasized this earlier. Okay, so this is just the header, and there's the listing of the subroutines, but the main body of the subroutines, so if you go to find link, as you can see I've been there, in match case, find next, okay, and next, and next, and next, and next, and next, and not there yet. Huh? Okay, link, label link. Okay, edit, find, link. We said find. There's plenty of links. Okay, I know what I'll do. Sorry for this. I know everybody's time is precious. You can so you can go like copy this whole thing, or maybe just this. Copy, and then you go edit, and then find. Oh, it was there by default. Okay, and all right. So I think I've got it. Find next. There it was. And here you see some comments that explain what they do. Some of you are able, I'm assuming, to, or most of you, to get to this point and read what link does. But what else we want to learn about, or you would like to learn about, is what the put angle does, what the put distance does. Okay, so if we go to put distance, okay, so put distance, what was it? Put distance, okay, and explains. It explains what dim is. So what it does, you saw it in action, and explains was the less than, greater than, being the arrow heads. And then there's a put angle above, so you need to read this as like a help explanation in order to customize, to change my source code to where you have to where you have the slider moving in the vertical direction. It's not in use, but you can instead of put this, or instead of reading the distance as is returned by the put distance, or the angle as is returned by put angle, you have these two subroutines, and it says variable distance, and you give the coordinates of two points, as well as their first and second time derivative, and it returns not just the distance, here I call it r, but also the first and second time derivative of that distance that changes, as well as an angle that the angle and its time derivative that changes. Okay, so I can have, for example, I can have that crank rotating, and I can supply that will be 0, 0, and 0, 0 is a ground point, and then the coordinates and their first and second time derivative of the endpoint of the crank, and recalculates for me. This will be, of course, the length of the crank, and 0. This does not change the length of the crank, but then it will be the angle and first and second time derivative extracted from knowledge of the 2 points. Now I can have points belonging to two bodies both moving, and I can observe how this distance, or rather extract the distance in first and second time derivative, as well as the angle and the change of angle, first and second derivative of that angle as the 2 points move. Okay, and then so that was for distance, and then for angular position, velocity, and acceleration, you may say this is the variable distance, angular position, velocity, acceleration. Likewise, supply 2 points, but does not give you the distance. It's just giving you the so you may say you can go around by just using variable distance and use only theta, d theta, dt theta. Angular position, velocity, and acceleration, what it does, it's returning just the angle and first and second derivative. And here you supply, like I said, 2 moving points here, and that will be an angle. I need to emphasize that this will be an angle relative to the ground. Okay, but I can supply 3 points, coordinates of 3 points, all moving, and it calculates the angle and their first and time derivative. Or I can and it would be the angle at B, formed with line AB and BC. Okay, but then I can supply 4 points, and it's going to measure the angle between the line AB and CD. Okay. So yeah, and neither of these are used, Veridis or any of these are used, but if you're interested, you can experiment with them. No graphical feedback, is just going to return values that you can write to a file and do things with them. Okay, and there's more to it. A lot of work that went into this. I'm not sure. Maybe will be appreciated to some extent by some of you. All right, so this being said, I'm stopping here. I'm sure this will be of help. Okay, so the slider has to move vertically, and then like in your project, and then the input data should be like for your project. All right, so 33 minutes of recording. Thanks for watching them.